Okay. Good morning, everyone. This is Jason Hu from Taiwan in Indigo Waters. And today I would like to share this paper, which is use of X-band radars to monitor small garbage islands. And this paper is published on a journal called Remote Sensing. And this journal is part of group MDPI. I think this group it's kind of controversial of recently because they have so many new journals and publish very quite amount of papers, and this paper has these impact factors. So I would like to mention this. If you are interested, you can take a deep look of this MDPI publishing group. They have so many different journals on different areas. So this paper is published in 2021, and after this paper, I found there are several, maybe two or three papers related to this radar technique to detect plastic debris, but I think those are too difficult to me. So I choose this one. It's more easier. And if you have time, maybe I can briefly, after this paper, I can briefly show you some figures of those latest paper related to this topic. So these two authors from Italy. Okay. So this is the abstract. So I simplify these abstracts. So the aim is to verify and demonstrate the possibility to using X-band radars to identify, discriminate, characterize, and follow small floating aggregations of marine litter, which they introduce these small garbage islands, SGIS, made by many of plastic debris. Radar measurement campaign was carried out on serious control release into the sea of SGI modules assembled in the lab using waste collecting along the beach near the port of Livorno in Tuscany, in Italy, where the X-band radar of the Institute of Bioeconomy of the National Research Council is installed. This preliminary work opening a new experimental avenues for the use of X-band radars also to monitoring plastic waste at seas. Furthermore, the result obtained suggests good perspective for the use of X-band radars, also for the study of coastal hydrodynamics on the local scale, as well as in area where it would be difficult to carry out measurement of applying other technologies. So I will go to the introductions. So the author mentioned about some basic knowledge of plastic debris and the importance of monitoring with different technologies, and finally they mentioned the remote sensing of marine litters. So more recently, remote sensing technique have also started to be used to monitoring marine litters, but no single remote sensing technique is currently able to return information with sufficient level of accuracy. So those remote sensing technique, including photographic images like camera on the drones or camera or the satellite images. And the next one is spectroscopy. So it could be micro or macro spectroscopy because different material like plastic or styrofoam, they have different spectroscopies profile. And next one is Raman spectroscopy, and they said it has potential to detect particles suspended below the sea surface. I think it is interesting because I only know Raman spectroscopy in a very micro plastic or in the laboratory levels. So I don't know if it can be used in the water surface. And this is SAR, synthetic aperture radars. I think it's kind of a norm of some military use, but it's interesting that it can detect high resolution information from the ocean surface, like finding the submarine or finding the sea currents or waves on the ocean surface. And usually it's adapted in vessels or in a satellite. Oh, so in this paper, the author used X-band radars. So X-band radars was born as a navigation tools, but it also works for remote monitoring for physical states of the sea, like to reconstruction the field of surface current or the bathymetry. It means the sea floor. And the potential of X-band radars used for macroplastic detection is they can have a real-time monitoring and a high spatial resolution and great flexibility, and it's widespread diffuse both on land and on ships. Okay, so here is a very basic concept about the idea of radars. So all the radars has a transmitter and a receiver. So the transmitter will send out a radio signals to emit a wave out, and when it touch a target, there will be a reflected wave, and will received by the receiver in this radar systems. So they will calculate the wavelengths and the time, the difference in times to generate the radar images, and use this data so they can detect distance. Okay, so content of this study use navigation radars to collecting the radar characterization of small garbage island. It's the amplitude of the signals. The signal interaction with wind and surface current. So let's go to material and method. So this is a study area in Lavers in Italy. So here, it's a city very nearby Pisa, yes. And it's a harbor city, and it has intense marine traffic. So in this harbor, you can see there are many big ships and many small recreational boat or sailboat here. And there is a building, I think it's a government building. And at the corner of this building, there's a radar here, X-band radar. So about this X-band radar, they provide some specifications. So this photo is not related to the journal's radar. I just searched on the internet, but I think it's looks quite similar. because it has a antenna and a base and some cable to transmit the data and the electricity. And so this is the radar parameters. So the peak power is this k watt, 25 kW, and it means the distance. If they have better power, greater power, it can transmit the radio to far distance. And also the antenna length is 2.7 meter, and which is, I think it's 9 feet. And the radar scale is almost 1 nautical miles. And the antenna rotation period, it means every 2.5 seconds, this antenna will rotate once. And the spatial images spacings is 3.5 meters, and antenna height 30 meters because it's on a building, top of the roof of a building, so it's 30 meters. So view angular sector is 190 degree north. I'm not sure this 190 degree is this degree because some of because the radar cannot detect the land areas, only detect the sea surface, and this is more than, I think it's just more than just about 190 degrees. 190 degrees. And about it, that's the signal. If the item is highly reflective, the signal will be red. If it's less reflective, it will be green and blue. For example, these are some man-made structures here, the wave breakers, the cement structure here, it will be greens, and some of them are blue. But if there are something are metals, like aluminum or some metal items, like these ships, it will be more red here. Okay, so this, and here they introduce how they make the small garbage islands modules. So they just go pick up garbage, doing the cleanup, just clean up the beach and collecting all the material they can have nearby. So they made one basic small garbage islands modules. It's called Target 0. So it's made by some reeds, drift, just like driftwood. There's a drift reeds, and put into use a plastic Tait to make a raft, and make this, and they give very details component of how they make this raft. So it's the area is 1 square meter, and they use 5 plastic bottle, 1 styrofoam box, 3 pieces of driftwood, 2 shoes, and 1 aluminum can, 2 plastic jars, 3 fishing net, 3 pieces of polyurethane foam, and 1 plastic sheet. So you can see here, there's a big styrofoam box here. So they think because they use all material from the marine debris, so it can represent a floating debris aggregate and floating together. And after they made this target 1, target 0, they also made other smaller items or other different modules. Like this is target 1. They use the same area, but they put all the material were plastic, like plastic sheet and plastic bottles. And this is target 2 and 3. they are just bottles. Like this is the 3 bottles tied together, and this is only 1 plastic water bottles. So a reference for determination of radar detection capability in terms of resolution and the radar cross-section RCS, which means if items has bigger RCS like this one or this one, they will have a greater detection of capability. I mean, possibility to be detected by the radar. Or if it's made by metals. Okay, so they do the measurement campaign. So they take a small boat and release these 4 targets on different place. They have 3 releases. So at each release, they all release these 4 targets and to collecting the radar signals. So the radar is here. So the first release, you can see it's very close. And the next one is a little bit far away. And the third, it's more far from the radar. So this is the photos during their first release. So you can see they take photos because it's quite close to shore. They take photos to identify where their target is. So you can find it's target 0, which one is the biggest raft with a lot of wood and plastic, and target 0, target 1, and target 2 and 3. Target 3 is the smallest, just 1 plastic bottles. And there are some structures inside this harbor, like there are some buoys. And this boat, I think this boat they use for release and I mean carry out all the experiments, field surveys. So because they have these photos, so they can compare with the radar's signals and to identify who is who. Like this one, it's target 0, target 1, like this. Okay, let's go to the result. So first is the radar signal intensity analysis. The sequence of radar data analysis procedures used to identify the target. So this is how they generate these figures. So first, they take photos to try to identify the relative position of these 4 targets, these 4 plastic items, and they will use a rectangular area to collect the image data from the radar, big radar signals. Like for this one, it's the target 0, the signal of target 0, and in every 16 instant of time. I'm not sure if the 16 instant of time, which directly means second. They didn't mention about the basic unit of the time here. But every 16 maybe unit or certain of time, they were collecting 1 image, focusing on that target. Like this is target 1, and because it was moving, so they keep tracking this target and try to like capture the photos of this target. And because they have these photos, these images, so they can generate this profile because they use the highest number in each square of these figures. Like for this one, the red red curve is target 1. So here, this peak means here because they have red signal here. And this one, the green one is target 2. And this, in this figure, this area here, they have a highest figure. So it generates this peak. So you can see there are different 1, 2, 3, 4 different target. And also they have a mean clutter, means the background scatters here, like the wind and the wave baseline here. But I think it's very interesting. They point out those peaks are not plastic islands. They are their boat, because the boat carry their debris and release. So you can see the boat first release the first target 0, target 1, and release target 2. So you can see they mentioned don't look at this peak. It means the boat. So the reflection, the signal only related to their target, the plastic islands, is the signal here at the middle of here or here. But you can still distinguish that they are different. Like the green one is different than the yellow and the blue. So because they have 3 release, so these are the result of other the second release and the third release. And on the second release, they go further away from shore. So they still take photos. And this is a small boat they use, and there are 1, 2, 3, 4 target here. So, and also those peaks are related to the boat, because sometimes the boat is too close to their target, so it will be put in a same square like this. Maybe this one is the target, their target, and this one is the boat. So actually the data is it's useless for that peak. So they mentioned this period is more important because all these outliners are the boat. And this is the third release, and because they go more far away from the shore, they found out there is no detection of target 3, which is just 1 plastic water bottles, because maybe it's too small or just cannot distinguish from the back scatters from the baselines. Okay, so the second experiment or analyze they do is the target shift and movement analyze. They try to calculate the movement of the target within the study area related to the first release. Actually, they do the different release. I just pick out the first release because I think it's quite similar. In this figure, it's begin of the first release of the target. And after certain of time, they found it's moving. Like originally, the target 2 is here, but now it's moved to here, and the target 1 is from here moved to here. So they can calculate the speed and the directions. These two parameters. So in this table 4, you can find the first and second release, and they calculate the speed of target 0 and target 1 moving, because these two are more like moving together, or because the weight and shape is quite similar. It's also all of them are in a 1 square meter reed raft, and tie some plastic items or other items on the surface. And target 2 and 3 are plastic bottles. Okay. So they also get some environmental or environmental information, especially for wind direction and wind speed, from this Tait station here, very close. So this is the data when they do the experiment of wind data, monitoring data. Then they also have these wave data from the regions. Okay, so in the discussion part of the first release, they said all the targets are clearly visible from the radar and can be clearly distinguished from the average sea clusters. But for the second release, all the targets are also visible, but due to the greater distance from receiving antenna, the intensity of radar signal back scattered by the target is lower. And the third release, they lost one target because it's too small. And for the target 0 and target 1, they were not influenced by very light wind blowing on the sea surface at the time of the experiment. And their displacement is substantially due to the surface current in the sea. As I mentioned, because they are heavier and they are more the portion, they have more portions sinking to the below the waters, so probably it's moved by the surface current. But for the target 2 and 3 were mainly influenced by the very light wind blowing in the areas. All this is due to the greater weight and target 0 and 1, which may less subject to the action of very light wind compared to the lighter target, which consider respective of the 3 plastic bottles tied together and a single plastic bottles. So for the conclusions, X-band radar distinguish the experimentation target within a maximum distance of 0.39 nautic miles from receiving the antenna. Beyond this distance, the intensity of signal received by radar mixed with average sea cluster. I think it's very a small distance, but we can think about it works at night, so probably it's a little bit, and then it works constant to 24 hours and or every 5 seconds or every 10 seconds. So it's different than other monitoring techniques. Okay, the next one is the measurement campaign represented in this report was carried out with a sea-state characterized by the absence of wave and almost complete absence of wind. So it's a very calm coast area, near shore areas, very calm waters. And in order to verify the sensitivity of the radar in optimal conditions, it follows that in the future, it will be necessary to conduct further measurement campaign also in the presence of the rough sea. Oh, okay. So this is my my slide. So do you have any questions?
Thank you, Jason.
You're welcome.
Let's have a discussion and opinion time.
Hi, Jason. Thanks for the talk. I'm Lincoln from Tangaroa Blue Foundation.
Yes.
Does the paper talk about where they think this might be useful? It seems, as you said, very close to shore and in very calm conditions. So are they expecting that this would be only useful in very certain cases, or what do they anticipate this being good for?
I think that they mentioned about some potential here, and I think for me, it's most interesting for me is for ships, because every ship has, I think almost every big ship has X-band and S-band radars. I think for small ship, they maybe only have one type of radar, but for bigger ship, like for the some bigger fishing vessels, you can see on the top of the ship, you can see they have this kind of equipment. Someone told me this to avoid the collection of another boat, and it also used for detection the direction of waves and the height of the waves, because the two different radars has different frequency and different wavelengths, so they have different resolution. For some kind of radar is better for detecting ships, and some radar is better for detecting the waves. That allows the ship, the driver, to avoid the big waves. So I think if some people can use this radar and to generate some kind of like monitoring, or try to let the ship collecting those data from marine debris, like just like other project, they mount a camera on the side of the boat, so that every boat or every ship can collecting data from all over the oceans. So that's my idea of this, because every ship has these radars. Maybe they can collect more data of floating debris. And other three advantage, I think it's real time, and if you can do at night. But I think because this is the first preliminary work, so the distance very short. Okay,
Thank you,
Thank you.
Jason.
that's my answer. Yes.
Then, Jason, could I ask one thing? Then we can avoid the radar on the ship, and when moving, I mean the ship is moving, we can detect the signal from the ship. We can send the signal to some object from the ship. I mean the radar on the ship, and receive the signal when the boat or big ship is moving. Do you mean that?
Yes. I think the purpose for this radar on the ship is to avoid hitting something. So the radar can calculate, this object is coming to us and in some certain of speed, and they will give a warning signal to the captains. So the original use for this radar is for that, to detect all the object upon the sea surface, and try to collect those informations, and to let the captain to make decisions.
Thank you for your answer. Then I would say we can use a ship of opportunity. If the ship has expanded radar, and they, when they survey other things, they can get record from the radar, and we can analyze that data and the debris data also. It's called ship of opportunity, something like that. Thank you.
Yes, I think all the harbors also have this equipment. All the commercial or fishing harbor or naval harbors, all of them have these different kind of X-band radars. And so I think if the authority of the radar system is willing to cooperate with, actually this is what we are doing right now. So we are trying to cooperate with, because we have some radar, it's for recreational use, like some radar in Taiwan, it's produce data and predict data or monitoring data of wave and wave height and wave direction for the servers, because people like to go surfing and they want to know it's a good wave or bad wave from their house, so that they can decide they should go to the beaches or not. So some research academia research institute put some radars in the surfing spot, try to make the real-time wave data for them. And now we are thinking maybe we can cooperate with those agencies to try to use this data to detect bigger macro debris in that areas.
Thank you. Other questions or opinions?
I have one. Can I share my screen now?
Okay,
yes.
please.
Yeah, when we prepare some suggestions for the government to construct a surveillance system for floating debris, we made this kind of concept to monitor the monitor and assess the risk of encounter of ship with floating debris. We can make this kind of a map using the data with the ship traffic and some data location or movement of floating debris. So when we construct this kind of system, we can make use of X-band radar or other remote sensing technology to get the floating debris patch on the surface of the sea.
Thank you. And other questions? If you have any questions or opinions, please turn on your microphone and tell us them.
Actually, I have a comment on that paper. So thank you, Sir Jason, for presenting the paper on the use of X-band radars to monitor SGIs. So the study provides valuable insights into the detection and tracking of waste in the ocean with promising prospects for monitoring efforts. So I appreciate the methodology employed, particularly the construction of SGI's module using the collected waste or plastic waste, which allowed for controlled experimentation and evaluation of the radar's capabilities. So one notable recommendation for the future research would be to assess the ecological impacts of SGIs on marine ecosystems. So understanding the consequences of this floating aggregation of plastic debris is very essential for developing comprehensive mitigation strategies. So by investigating the interactions between SGIs and marine organisms, researchers can evaluate the potential harm caused by entanglement, ingestion, or habitat alteration. So this ecological perspective would provide a more holistic understanding of the impacts of plastic waste on marine life and also the ecosystem. So however, it is important to address the potential limitation of the study's limited generalizability. So the focus on a specific geographic location and controlled experimental setup may restrict the broader applicability of the findings. So expanding the research to include different oceanic regions with varying environmental conditions would enhance the validity and relevance of the results. And assessing the performance and limitation of X-band radars in diverse settings, it will contribute to a more comprehensive understanding of the challenges associated with monitoring plastic waste in different marine environments. So all in all, this paper contributes a valuable insight into the use of the aforementioned radar for monitoring SEIs. However, the future research efforts should incorporate an ecological assessment of SEI's impact on marine ecosystem and expand the study scope to encompass different geographical regions and environmental conditions. So by addressing all these aspects, we can further advance our knowledge and develop effective strategies to mitigate the ecological and environmental consequences of plastic waste in our oceans. That's my comment. So
Okay.
again, thank you. Thank you.
Thank you. Do you have any questions or opinions for the paper or other things related to the remote sensing technology?
Can I have maybe 5 or more minutes to share some figure of other 2 papers related to this topic?
Yeah, of course. So we can wait. And
Okay.
for the moment, I agree with the art. This paper, in the conclusion, they described about the limitation of this study. The condition was so calm and no wind, and the distance is too short, like that. I would add say one thing. I would add one thing. And they already know what object is there on the ocean, and in natural environment we don't know what are in the ocean. So the result from real environment would be very different from this result, and would be difficult more than this preliminary study.
Okay, I would like to quickly share 2 papers, like some kind of like follow-up of the paper I share. So this one is in a laboratory. They tried 2 different radars. One is called C-band and another called X-band. The difference between this radar is the frequency and the wavelengths. So they try to use this radar in the laboratory in a water tank and put some plastic garbage on the water surface and make different waves and try to distinguish the difference. So you can see these are the radar antenna here and in a laboratory, and they have some assumption that if the water is very calm, the radar reflection will like this, and if the surface of plastic covered by a very slightly waters get wet, so the reflection will different, and this kind of, and if it's transparent and cause another reflections, or if there are some small waves here, it will be another different. So this is, I think it's too complicated. I can show you the photos here. So there straws. They put so many plastic straws here and make different waves. And they put different plastic lid, like lid of salad containers, and try to use in the laboratory, try to detect the reflection of the radar. And the results shows that the X-band radar works better than the C-band radar. The X-band is better than the C-band, something like that. And they give a lot of like formula how to generate or analyze those signals. And another is from the remote sensing. They use a very popular Signature-1 SAR satellite. I think they have I think these satellites it's launched by the UN, and it's open data and it's very useful for many kind of environmental studies. So they use this SAR, it's sensitive patron radar data, try to detect a very big floating debris in the water dam. So you can see here it's a lot of plastic and driftwood in the water dam here. So they try to collecting the images, the radar images, and try to analyze the difference between those floating debris and the waters, something that is like that. So yes, like this. Okay, so these are two. One is in a laboratory, and another is people use this technique to try to find marine debris. Okay, that's it.
There'd be no questions anymore. And when I read this paper, I thought if we set this radar on the river mouth, and then after the heavy rain, they will discharge the water. When the water is running, we cannot detect the object because of the clouds or other not calm conditions. But later, in a few days, education shows us just before, we may detect a lot of debris and plastics, but the debris is mixed with trees and the metals. I mean, the plastic is mixed other things. Then in the case, can we detect plastics or other debris from the trees or triggers? I wondered. That's my opinion. July 1st, we'll have a next seminar and we'll present a paper. And thank you for participating in the seminar, and see you next seminar.